carbon dioxide gas enters a water-cooled compressor at the initial conditions of pressure at state 1 is 15 pounds per square inch and temperature at state 1 is 50 degrees Fahrenheit and is discharged at the final conditions of pressure at state 2 is 520 pounds per square inch and temperature at state 2 is 200 degrees Fahrenheit. The entering carbon dioxide flows through a 4-inch diameter pipe with a velocity of 20 feet per second, and is discharged through a 1-inch diameter pipe. The shaft work supplied to the compressor is 5,360 British thermal units per mole. What is the heat transfer rate from the compressor in British thermal units per hour, given that enthalpy at state 1 is 307 British thermal units per pound mass, given that specific volume at state 1 is 9.25 cubic feet per pound mass, given that enthalpy at state 2 is 330 British thermal units per pound mass, and given that specific volume at state 2 is 0.28 cubic feet per pound mass. You have the given values for both state 1 and state 2. Area of a pipe is equal to pi times the diameter of the pipe squared divided by 4. Solve for the area of the entering pipe, which is state 1, and the area of the discharged pipe, which is state 2. Use the conversion of 144 square inches equals 1 square foot to get area in terms of square feet to have consistent units with other values in this problem. Mass flow equals area at state 1 times velocity at state 1 divided by specific volume of state 1, plug in the known values. Mass flow equals 0.18868 pounds mass per second. Velocity of state 2 equals the mass flow times specific volume at state 2 divided by the area at state 2, plug in the known values to solve for the velocity of state 2, which is determined to be 9.686 feet per second. Using the equation change in enthalpy plus change in velocity squared divided by 2 times the g-c conversion factor plus the acceleration of gravity times change in elevation divided by the g-c conversion factor equals heat transferred plus work on the system. Since elevation is not mentioned, assume change in elevation is 0. Let's focus on the part of the equation regarding change in velocity squared divided by 2 times the g-c conversion factor. Velocity at state 2 squared minus velocity at state 1 squared divided by 2 times the g-c conversion factor. The g-c conversion factor is 32.174 pound mass times feet divided by pound 4 seconds squared. Plug in the known values to solve for this part of the main equation. When simplified, the end value is negative 4.7582 feet pound force per pound mass. Use dimensional analysis to get this value in British thermal units per pound mass to be consistent with the units for the enthalpy values. This value is determined to be 0.006146 British thermal units per pound mass. The change in enthalpy is the enthalpy at state 2 minus the enthalpy at state 1, which equals 23 British thermal units per pound mass. Shaft work is being supplied to the compressor at 5,360 British thermal units per mole. Because this problem deals exclusively with British units, assume the mole is for pound moles. The molecular weight of carbon dioxide is 44.01. Use dimensional analysis to get this value in units of British thermal units per pound mass. This value is determined to be 121.79 British thermal units per pound mass. Rearrange the main equation to solve for the heat transferred. Plug in the derived values and solve for heat transferred. The heat transferred is negative 98.80 British thermal units per pound mass. The value is negative, because heat is leaving the system. In this case it is heat transferred from the compressor. The problem wants the heat transfer in terms of British thermal units per hour. The new derived value for heat transfer can be converted to British thermal units per hour using the mass flow and converting seconds to hours. Solving for the heat transfer rate in terms of British thermal units per hour equals negative 67,110 British thermal units per hour. The value is negative because it is heat leaving the system, which is heat produced by the compressor. This is the final answer for this problem. Great job, you are improving your understanding of thermodynamics. If you like this video, please subscribe, like, comment, and share. Subscribing and sharing helps a lot and is greatly appreciated. If you missed anything, please rewatch this video. In the upper right is an ultrasound detection of a methane leak in a reciprocating compressor, which you may find interesting. Please check out other videos on this channel also. If you have any recommendations for future videos, please leave a comment. Thank you for watching. Have a nice day.